one, 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 give me one, 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 give me one, 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 give me one, 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 give me one, 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 give me one, 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 give me one.
Good morning, Manandal. Myself Sreevani, working as an assistant professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal, Hyderabad. So in today's lecture, we are going to learn about some of the questions, how we are going to write in the examination point of view, the short answer way and the long type and analytical type questions, which are covered in the module 5, that is UHF transmission lines and applications in electromagnetic waves and transmission lines. So coming to the short answer type questions in UHF transmission lines and applications. Well, UHF stands for ultra high frequency line transmission lines, and followed by some of the applications related to the questions we will be discussing in this particular lecture. So coming to the first question, what is meant by standing wave? Generally it is represented with S, and standing waves are the waves which consisting of two traveling waves. One is incident wave and another one is reflected wave. Whatever the wave which strikes the boundary or touches the boundary, that is completely reflected back to the same medium case, then standing waves are produced. Then those are called as stationary waves also, right? So standing waves are the waves which consisting of two traveling waves. One is incident wave and the other one is reflected wave. Generally we are representing the notation for this standing wave ratio as S, and the range of this will be given by 1 to infinity. The standing wave ratio S is to be ranging from 1 to infinity. Then define reflection in a transmission line. So the term reflection which is occur in the transmission line can be defined as, means whatever the wave which is touches the boundary or strikes the boundary, means when the incident wave touches the boundary, part of this incident wave is reflected back to the same medium and part of this incident wave is transmitted to the next medium in the case of waves, electromagnetic waves. Now coming to the reflection in the case of transmission lines, means when the characteristic impedance of the transmission line Z0 and the load impedance of the transmission line ZL are same, then this is the case. The line is said to be properly terminated. When these two are not equal to, Z0 is not equal to ZL case, then reflection occurs. Right? So Z0 is said to be characteristic impedance of the transmission line and ZL be the load impedance of the line. Then define refraction in transmission line. As we have seen, when the incident wave touches the boundary, part of the wave will be transmitted to the next medium, part of the incident wave is reflected back to the same medium. That transmitted wave is also called as here refracted wave. This is the way the refraction can be occur in the case. Depending upon this reflection and refraction, we'll be considering two laws. One is Snell's law of reflection and Snell's law of refraction in the case of electromagnetic waves. Now here refraction is related to the transmitted wave in the transmission lines. Give the expression for reflection coefficient in transmission line. So generally this reflection coefficient gamma is defined as, it is the ratio of the reflected wave field strength to the incident wave field strength. Coming to the transmission lines, it is the difference between the maximum voltage to the minimum voltage, and it is given by in terms of load impedance, and the characteristic impedance can be given by here gamma equal to ZL minus Z0 by ZL plus Z0. Right? Reflection coefficient of a transmission line, generally it is represented with the gamma, and it is given by the ZL minus Z0 by ZL plus Z0, where ZL be the load impedance of the transmission line and Z0 be the characteristic impedance of the transmission line. And the range of this reflection coefficient is, means if you want to express this reflection coefficient in terms of its magnitude and the phase functions, means magnitude form can be written as modulus of gamma and the phase function can be written as e power j phi. Right? So gamma can be written as here ZL minus Z0 by ZL plus Z0. And as we know that the range of this reflection coefficient will be ranging from 1 to 0 to 1. 0 is less than or equal to modulus of gamma is less than or equal to 1. This is the way the reflection coefficient is ranging from 0 to 1. Next, what are the different types of standing wave ratios in the transmission lines? So there are two different cases in the standing wave ratios. One is VSWR, that is voltage standing wave ratio, and the second one is CSWR, voltage standing wave ratio and current standing wave ratio. So different types of standing wave ratios in the transmission lines occur in two cases as VSWR and CSWR, where VSWR means it is the ratio of the V maximum means V maximum by V minimum, that nothing but Vi plus Vr by Vi minus Vr. Means if you consider the ratio of incident wave to the reflected wave voltages, then it will be regarding as voltage standing wave ratio. Similarly, current standing wave ratio means it is the ratio of the current relations, that is Ii plus IR by Ii minus IR. Right? So depending upon this, standing waves can be considered as stationary waves. Those are the waves which consisting of two traveling waves. One is incident wave and the other one is reflected wave. Then coming to the reflection means if ZL is not equal to Z0 case, characteristic impedance is not equal to the load impedance case, reflection occur, then refraction can be occurred case, that is Z0 equal to ZL case. Then expression for the reflection coefficient is given by gamma equal to ZL minus Z0 by ZL plus Z0, and VSWR. Two types of the standing wave ratios or voltage standing wave ratio and current standing wave ratio. Next, specify the relation between voltage standing wave ratio and the reflection coefficient in transmission line. So generally this VSWR is represented with S, voltage standing wave ratio is represented with S, and the reflection coefficient is represented with gamma. Then relation between these two means S in terms of gamma can be written as 1 plus gamma by 1 minus gamma, and reflection coefficient gamma in terms of S means S minus 1 by S plus 1. Right? Relation between VSWR and reflection coefficient can be written as gamma equal to S minus 1 by S plus 1 and S equal to 1 plus gamma by 1 minus gamma. Then, what is the use of impedance transformation? To avoid reflections, first point, and to get the maximum power transfer. What is the use of impedance transformation? So there are two main advantages over this impedance transformation, that is to avoid reflections in the transmission line and to get the maximum power transfer case we use impedance matching. Then what is the use of Smith chart? Generally Smith chart is a graphical tool which is used to represent reflection coefficient gamma and the VSWR as the standing wave ratio as S. So by mathematically we can write the formulas as gamma and S means S equal to 1 plus gamma by 1 minus gamma and gamma equal to S minus 1 by S plus 1. Whereas in order to represent it in the same values on the graph, we used to consider one graphical tool called Smith chart. Right? So in order to measure with the help of graph, we used to measure reflection coefficient gamma and the standing wave ratio S. Along with this input impedance of a transmission line, we use the chart called or graphical tool called Smith chart. Next, describe the relationship between the short circuited impedance, open circuited impedance and characteristic impedance. This short circuited impedance is generally denoted with ZSC. Short circuited impedance can be represented with ZSC and open circuited impedance is represented with ZOC, whereas characteristic impedance is given by Z0. And the relation between 3 can be written by here Z0 equal to root over ZSC into ZOC. Characteristic impedance of a transmission line Z0 is equal to under root of ZSC into ZOC. Okay. So generally the short circuited impedance is represented with Z, and for short circuited it is ZSC, and for open circuited it is ZOC, and the characteristic impedance as Z0. Then the relation between 3 is given by here Z0 equal to root over ZSC into ZOC. Next, coming to the long answer type questions. So in exam point of view, how we are going to return answer type questions or long answer type questions which are covered in the ultra high frequency transmission lines and applications. Explain the principle of impedance matching with quarter wave transformer. So generally, so before going to write the equation for the quarter wave transformer of a input impedance transmission line, then we need to define first impedance matching. When the impedance matching occur, or what is the need for the impedance matching? To get the maximum power transfer and to avoid the reflections in a transmission line, we used to consider here one of the method called impedance matching. This is the case ZL is equal to Z0. Means load impedance of the line is equal to the characteristic impedance of the transmission line, that is ZL is equal to Z0 case impedance matching occur. And in order to derive the condition for the property which is associated with the quarter wave transformer, means depending upon the wavelength, there are three different types of lines or exist. One is lambda by 2, and another one is lambda by 4, and next one is lambda by 8. So half wavelength line, quarter wavelength line, and eighth wavelength line. Depending upon all this, the first one is given by here quarter wave transformer type. So in this, now to write the analytical part related to this, we need to consider input impedance of a lossless transmission line. In that, the formula is given by mathematically we can write it as Z0 into ZL plus JZ0 tan beta L by ZL plus Z0 plus JZL tan beta L is equal to. So here it consisting of only beta means it is an example for the lossless line. There is no attenuation constant in that. See, if the attenuation constant alpha is exists in the equation, then there must be some loss in the signal. Hence, that lossless line becomes lossy one. Here, it consisting of only imaginary means there is no attenuation constant. Hence, it resembles the equation for it as lossless one. Okay. So this is the input equation for the lossless transmission line. In there, we just consider quarter wave transformer type. Means L is equal to length need to be considered as lambda by 4. And as we know that beta formula can be given by 2 pi by lambda. Why? Because the wavelength, how we define wavelength means according to after every 2 pi radians, the phase is going to change. According to that, lambda can be written as 2 pi by beta. Now from this, beta can be considered as 2 pi by lambda. Now substitute in case of beta by 2 pi by lambda and L by lambda by 4 over here, then it becomes Z0 into. So before going to substitute over here, first we need to multiply beta L. So beta value is 2 pi by lambda and L is lambda by 4. Then 2 gets cancelled, lambda gets cancelled. Beta L is equal to pi by 2 is obtained. Now from this, if you take tan beta L as common here, then it becomes ZL by tan beta L plus JZ0 by here in the denominator also, if you take tan beta L as common, then Z0 by tan beta L, then plus JZL. Right? So here tan beta L gets cancelled, and if you substitute beta L by pi by 2 over here, means tan pi by 2, that is tan 90, its value becomes infinity. So something by infinity case, the total term becomes 0. Now the numerator and denominator, both the terms becomes zeros. Hence, Zn is equal to Z0 into JZ0 by JZL. Okay. So imaginary terms JZ get cancelled, which is equal to Z0 square by ZL is to be obtained. So this is the way the principle of impedance matching with the quarter wave transformer need to be analyzed by mathematical equations. Next, explain the significance and utility of lambda by 8, lambda by 4 and lambda by 2 transmission lines. So in order to use all the three wavelength lines equations, we must consider again the input impedance equation, that is Zn is equal to Z0 into ZL plus JZ0 tan beta L by Z0 plus JZL tan beta L. In each and every case, we just substitute beta is the general formula is given by 2 pi by lambda, and every time L value need to be changed, that is from lambda by 2 to lambda by 4 to lambda by 8. Then every time if you substitute, one time if you consider lambda by 2 as the L value, and another time if you consider lambda by L value as the lambda by 4, and another time for the 8th wavelength line if you consider lambda by 8, then beta into L need to be multiplied. Then if you substitute beta L by or here the values, then we will be relate the three relations with respect to the input impedance of a transmission line. Right? This is the way the significance and the usage of the lambda by 8 and lambda by 4 and lambda by 2 lines in the impedance matching case we will analyze. Next, describe the construction of Smith chart and give its applications. As we know that now to measure the reflection coefficient and standing wave ratio, we use one of the method called a graphical method is represented with help of Smith chart. Basically, it consisting of constant resistance circles, and constant reactance circles. Constant resistance circles and constant reactance circles. So here, in order to design this Smith chart, we use normalized impedance plane. That normalized impedance plane is generally represented with a small z, and it consisting of real part as well as the imaginary part. Real part is represented with the constant resistance circles, and imaginary part is represented with the x and for constant reactance circles. So for all the constant resistance and reactance circles, we just vary different R values for the resistances and different X values for the reactances. Then with the help of this, we will draw the Smith chart or graphical method now to find reflection coefficient and standing wave ratios. One of the important one, our graphical method called Smith chart. Right? In order to draw this, the main two circles are required called constant resistance circles and constant reactance circles. Then, derive the relation between reflection coefficient and the standing wave ratio. So, in order to derive this one, as we know that reflection coefficient gamma is given by ZL minus Z0 by ZL plus Z0. Okay. So from this, if you find our ZL is equal to, where ZL be the load impedance of the line and Z0 be the characteristic impedance of the line, right? So in terms of this one, if you multiply, means gamma into ZL plus gamma into Z0 equal to ZL minus Z0, right? So if you separate the ZL terms and Z0 terms separately, then gamma ZL minus, if you take this gamma 2 here and the gamma Z0 minus plus Z0 is equal to ZL minus gamma into ZL can be written. So if you take here Z0 as common, then gamma plus 1 is equal to, if you take here ZL as common, then it becomes 1 minus gamma, right? So in order to write the standing wave ratio, then it is to be considered as that becomes Z0 by ZL or equal to 1 minus gamma by 1 plus gamma, or if you consider the output quantity to the input quantity, let it be load to the characteristic impedance, that is ZL by Z0 is equal to 1 minus 1 plus gamma by 1 minus gamma. So this can be considered as a standing wave ratio that is represented with S. Right? The relation between reflection coefficient gamma and the standing wave ratio S need to be expressed as gamma equal to ZL minus Z0 by ZL plus Z0, and reflection coefficient gamma in terms of standing wave ratio is given by S minus 1 by S plus 1. Next, derive the expressions for input impedance of a uniform transmission line terminated with load impedance. Right? Input impedance of a transmission line that is represented with Zin. It is the ratio of the input voltage to the input current, and it is expressed as next. Hence, discuss the properties of a quarter wavelength line and half wavelength lines, assuming the line to be lossless. So first we have to express this one in terms of lossless transmission line, that is given by Z0 into ZL plus J Z0 tan beta L by Z0 plus J ZL tan beta L. So for the properties of quarter wavelength line, means first L value is equal to lambda by 4 and beta equal to 2 pi by 4, 2 pi by lambda. Then if you multiply these two, beta into L, then it becomes pi by 2. Then if you substitute here tan beta L by pi by 2, then input impedance Zin can be written as Z0 square by ZL. Means input impedance of a transmission line when we consider quarter wavelength line, then input impedance and the relation between the characteristic impedance is given by Zn is equal to Z0 square by ZL. Similarly, if we consider L is equal to lambda by 2 and beta equal to 2 pi by lambda, this is the case. We multiply 2, then 2 pi by lambda into lambda by 2, then 2 gets cancelled, 2 gets cancelled, beta L is equal to pi. Right? So if you substitute in this equation tan beta L by pi, then tan pi becomes 0. Why? Because tan pi is nothing but tan theta is nothing but tan pi can be written as sin pi by cos pi. Then this pi value need to be sinusoidal signals becomes 0, hence it becomes 0. Now if you substitute over here, Zn is equal to Z0 into ZL plus 0 by Z0 plus 0. Now Z0 into ZL by Z0 can be obtained. 2 gets cancelled. Zn is equal to ZL. This is the case for a length, half wavelength line case. Input impedance and the load impedance are the exactly same. Now if we consider quarter wavelength lines, then it becomes Zn is equal to Z0 square by ZL. Next, derive the expression for input impedance of a lossless transmission line. Hence, evaluate ZOC and ZSC. Also sketch their variation with line of length. Right? So, for a lossless transmission lines means attenuation constant. So, in order to derive the equation for this, we just consider first propagation constant gamma. That can be written as attenuation constant alpha and the phase constant as beta. Now, for a lossless one means that loss is indicated with attenuation. Means if alpha equal to 0, gamma becomes J beta only. Right? This is the case. Input impedance of a transmission line can be written as Z0 into ZL plus JZ0 tan beta L by Z0 plus JZL tan beta L. This is the equation for the input impedance of a lossless transmission line. And to evaluate output open circuited impedance and short circuited impedance, then the relation between the characteristic impedance on the two open circuited as well as the short circuited can be obtained as Z0 is equal to root over ZSC or ZOC into ZSC. Right? This is the way we can write the equations for lossless transmission lines and the evaluation of open circuited as well as the short circuited impedances. Next, explain how an open circuit line acts as a circuit element. So this comes under UHF circuit elements, UHF lines as circuit elements. In the case of theory classes lectures, we have discussed about UHF transmission lines as circuit elements. Suppose if you consider when the source impedance is here and the followed by one load impedance need to be connected at load side. So this is the case. Open circuited means if you connect the load across this one, we are representing it with ZL, and the ZL is equal to the, for an open circuited line case, IL is equal to 0. If we connect over here a load impedance term as ZL, then we need to consider the current flows through that as IL and the voltage drop across this will be considered as VL. For an open circuited line, then we are assuming it as IL is equal to 0. Now IL is equal to 0, then load impedance ZL can be considered as ZL is equal to VL by IL. Means if we substitute over here IL by 0, then ZL becomes infinity. Now this is the case if ZL is equal to infinity, then input impedance of a transmission line can be written as Z0 into ZL plus JZ0 tan beta L by Z0 plus JZL tan beta L. Right? So if we substitute over here ZL by infinity, then how the equation need to be simplified. This is comes under open circuited line as circuit element. Then explain how a short circuited line acts as a circuit element. So in order to find this short circuited line, again we used to consider here the load impedance is to be connected at the load side and the characteristic impedance need to be obtained as per here. Then this is the case. Again, the current flows through this is represented with IL and the voltage drop across this will be equal to represented as with VL. Then load impedance ZL can be written as here ZL is equal to VL by IL. Means for a short circuited line, this can be considered as shorted one. Why? Because we are assuming here VL is equal to 0. If you are assuming VL is equal to 0, then ZL is equal to 0 for the case of short circuited line. So similarly in the open circuited line case, we just remove this one ZL. Then here open circuited terminus case, we are assuming load impedance for the case as here infinity, and for the short circuited case ZL is equal to 0. Depending upon the load voltage and the load current, we will be analyzing the open circuited line as a circuit element and short circuited line acts as a circuit element. Then explain the construction of Smith chart. So to write the concentric resistance circles as well as reactance circles, now to construct the Smith chart, we used to follow some procedure. First one is related to the constant resistance circles, and the second one is constant reactance circles. So to draw the constant resistance circles, we need to vary different values of R. At the center, R equal to some with radius, at some center, we will draw some concentric circles, but with a representation of resistance circles. And similarly, for different values of X, means the different values of X may be the reactance values, and with the center, we will draw some of the arcs, which are imaginary lines representing as arcs, which are combined, and those arcs are combined with the circles. Then it looks like exactly, means the graph will be like this. All the concentric circles are represented as like this. Then all the constant reactance circles are represented as like this. Then it will be looks like exactly a Smith chart, right? So with the help of Smith chart, we can find the reflection coefficient gamma and the standing wave ratio S. Right? So theoretically also we'll measure the reflection coefficient gamma and the standing wave ratio as S using the formulas as gamma equal to ZL minus Z0 by ZL plus Z0, and The standing wave ratio is equal to 1 plus gamma by 1 minus gamma. Then write short notes on the following: reflection coefficient and VSWR. As we know that reflection coefficient gamma is given by here, that is in terms of load impedance and the characteristic impedance, can be written as gamma equal to 1 ZL minus Z0 by ZL plus Z0, and the range of this will be equal to, means if ZL is equal to Z0, if ZL is not equal to Z0 case, how the reflection coefficient values are to be ranged, means range of this reflection coefficient gamma to be ranging from 0 to 1. And VSWR is ranging from generally, means now we want to express the standing wave ratio S in terms of reflection coefficient, means that is given by 1 plus gamma by 1 minus gamma. Now if we substitute gamma by 0 one time and gamma by 1 one time another time, then we'll be getting here the range of the standing wave ratio will be ranging from 1 to infinity. Okay? So these are the two interrelated terms in the transmission lines. One is reflection coefficient gamma and the another one is standing wave ratio S. There are two types of standing wave ratios are there. One is related to the voltages, we are representing it with VSWR, and if you are talking about currents, then it is to be written as CSWR, current standing wave ratio and voltage standing wave ratios. Now coming to the analytical type questions. So mathematically, how we are going to solve the problems which are given in the UHF transmission lines and the applications, right? So find the characteristic impedance of a transmission line at 1600 Hz if the following measurements have made on the line at 1600 Hz, ZOC and ZSC, right? So to find the characteristic impedance, means characteristic impedance is generally represented with Z0 in a transmission line, and with the frequency, line frequency is also given, that is 1600 Hz, and open circuited impedance is given as 750 and short circuited impedance is given as 500. So to find the characteristic impedance and the relation between characteristic impedance Z0, open circuited impedance ZOC, and the short circuited impedance as ZSC can be written as root over ZSC into ZOC. So that equal to root over 750 into 500. Simplify this one, then Z0 value need to be obtained, then which is to be given by here Z0. In general, it is measured in terms of ohms, right? So this is the way we can solve the characteristic impedance of a transmission line if the open circuited impedance and the short circuited impedance are to be obtained, multiplied. Then a transmission line of length 0.4 has a characteristic impedance of 100 and is terminated by a load impedance of 200 plus J180 ohms. Find the reflection coefficient, VSWR, and input impedance of the line. So a transmission line of length means L value is given, L is equal to 0.4 meters, and the characteristic impedance means this can be considered as Z0, that is given by 100 ohms, and it is terminated by a load impedance, means ZL is given as 200 plus J180 ohms. Then to find the voltage reflection coefficient, means gamma equal to ZL minus Z0 by ZL plus Z0 is the formula. So load impedance is given as here 200 plus J180 by 180 minus J0. Z0 is 100 by 200 plus J180 plus 100 is given. According to the formula, ZL is 200 plus J180 and Z0 is 100. So ZL minus Z0 by ZL plus Z0, if you solve this one, then 200 minus 100 becomes 100 plus J180 by 200 plus 100 become 300 plus J180. Then to find this, means gamma can be generally expressed as gamma equal to modulus of gamma into e power j5. To find the magnitude of this one, we need to convert the complex form of, means rectangular form, into polar form. By converting this one, the numerator form can be converted into R1 at an angle of theta 1 by the denominator R2 at an angle of theta 2 need to be obtained. To simplify the gamma means modulus of gamma magnitude, we used to consider R1 by R2 becomes an R, and this one can be considered as angle theta 1 minus theta 2 be considered as theta. Right? Finally, this gamma can be expressed as modulus of gamma into e power j phi or R at an angle of theta, where this R must be ranging from 0 to 1 only. Why? Because reflection coefficient gamma is to be vary in terms of the range will be 0 to 1 only. So from this, you are supposed to consider the magnitude or the value which is to be obtained in the range of 0 to 1 as to be the value of gamma. Next, in order to find voltage standing wave ratio, we just consider S is equal to 1 plus gamma by 1 minus gamma. Whatever the magnitude which we are got it from the reflection coefficient, that value we have to substitute over here then to get the value of the standing wave ratio. And this value need to be ranging from 1 to infinity. In between, any value need to be obtained for voltage standing wave ratio. Similarly, input impedance of the line. So to find the input impedance of the line, we use here the formula as Z0 means Zin is equal to, the formula is given by Z0 into ZL plus JZ0 tan beta L by Z0 plus JZL tan beta L. So in this, you just substitute ZL by 200 plus J180 plus J Z0 as 100 tan beta into L. So how we will find beta into L value means a transmission length of the line is given as 0.4. Means L value is to be obtained as L is equal to 0.44 meters, and first we have to consider beta L value. Beta need to be considered as 2 pi by lambda, and into L value is 0.4. Right? So if you substitute over here beta L by 0.4 into the total thing, then Zin need to be obtained. Generally, it is to be measured in terms of ohms. Right? As we have considered this Z0 and ZL values are from the given as 200 plus J180 and Z0 as 100 ohms. Right? So voltage now to find the voltage reflection coefficient gamma equal to ZL minus Z0 by ZL plus Z0 is supposed to use, and VSWR value in order to find S is equal to 1 plus gamma by 1 minus gamma, or here this one input impedance of the transmission line, we use this as the formula. So to find here beta L is equal to 2 pi by lambda, then sometimes we used to consider the velocity formula as, that is velocity equal to omega by beta, and if you substitute over here this omega value, omega into beta, then in place of beta by, if you substitute 2 pi by lambda, then all need to be multiplied over here tan beta L, then you're supposed to get some tan function value. Then from that we'll be considering again, means in the numerator part separately again how we have evaluated over here. First we need to transform the numerator part into polar form, again in the denominator part into polar form, then both the magnitudes of the polar forms need to be divided and the phase angles need to be subtracted. Finally, we are supposed to get R at an angle of theta. But Zin can be expressed in terms of complex form, means x plus iy form. Again, we have to convert that polar form into rectangle form. Next, calculate the characteristic impedance of a quarter wave transformer if a 120 ohm load is to be matched to a 75 ohm line. Right? So, quarter wave transformer, if a 120 ohm load means ZL value is given as 120 ohms matched to a 75 ohms, means Z0 is equal to 75 ohms. Then characteristic impedance can be ZL is equal to and Z0 is equal to match to A, means ZS can be considered as here ZL and Z0. So this can be considered as input impedance or ZSC or characteristic impedance no, that can be considered as with Z. So for the input impedance of a transmission line or characteristic impedance of the transmission line, that is represented with here Zn is equal to Z0 square by ZL. Why? Because for a quarter wave transformer, we just consider L is equal to lambda by 4 and beta value to be 2 pi by lambda. Then input impedance of a transmission line can be substituted over here as Z0 into ZL plus JZ0 tan beta L by Z0 plus JZL tan beta L. Then if you substitute over here everything, then tan beta L value becomes infinity. Then that is the case. Z0 into Z0 need to be multiplied, and in the denominator we just left over here by ZL value. So Zn is equal to, or characteristic impedance of the quarter wave transformer can be obtained using the formula as Zn is equal to Z0 square by ZL. So Z0 value is to be obtained as here 75 ohms, means 75 into 75 by ZL value is given by 120. So by simplifying this one, you're supposed to get some finite amount of value need to be obtained as the characteristic impedance of the quarter wave transformer, and generally it is to be measured in terms of ohms. Next, a transmission line having a 50 ohm impedance is terminated in a load of 40 plus J30 ohms. Describe the voltage standing wave ratio. So voltage standing wave ratio means simply you just consider it as VSWR, or the notation as S is equal to 1 plus gamma by 1 minus gamma. So in order to find this S, we should express this one in terms of reflection coefficient gamma. So to find first, in order to find this voltage standing wave ratio, first we have to evaluate the reflection coefficient as gamma. That can be written as gamma equal to ZL minus Z0 by ZL plus Z0. So here ZL value is given as 40 plus J30 and Z0 value is given as 50 by then 40 plus J30 plus 50. So upon simplifying this one, we will be getting the value as gamma equal to modulus of gamma into e power j5. And this modulus of gamma need to be considered as the gamma for this, and finally S is equal to 1 plus gamma by 1 minus gamma need to be obtained. Here reflection coefficient doesn't have any units, and similarly standing wave ratio is also doesn't have any units. Okay? So as the reflection coefficient is ranging from 0 to 1 and the standing wave ratio need to be ranging from 1 to infinity, those two ranges are to be perfectly matched. Next, a lossless transmission line with Z0 equal to 50 ohms is 30 meter long and operates at 2 megahertz, and the line is terminated with a load of 60 plus J40 ohms, and if U equal to 0.6 C of the line, then find first the reflection coefficient gamma, that equal to ZL minus Z0 by ZL plus Z0. Now substitute over here ZL value as 60 plus J40 minus 50 by 60 plus J40 plus 50. So upon simplifying, you will be getting the value gamma equal to in the range of 0 to 1. Suppose if my gamma value need to be approximately equal to 0.3 is to be obtained. How this 0.3 has come means, in the numerator if you have a complex variable as a real term and imaginary term, and in the denominator also we'll be having, means its values looks like 60 minus 50 as 10 plus J40 by 110 plus J40 is to be obtained. So to find the some magnitude of this one, we need to transform this rectangular form into polar form by converting R1 at an angle of theta 1 by R2 at an angle of theta 2. By converting this to means R at an angle of theta, again this R need to be considered generally as the magnitude of this gamma. Similarly, the standing wave ratio, so that can be written as S is equal to 1 plus gamma by 1 minus gamma. So whatever the value which we have got here, it has the magnitude, and that need to be considered for the value as gamma, and finally we are supposed to evaluate the value for the S. Next, input impedance. To find the input impedance, the formula is given by input impedance is equal to Z0 into ZL plus JZ0 tan beta L by Z0 plus JZL tan beta L. Okay, which is equal to. Now in order to simplify, Z0, ZL, everything is there. Now we need to find beta L value. So L value is given as L is equal to 30 meters long and beta need to be evaluated. So generally in order to find beta equal to 2 pi by lambda. So to find this lambda, we use another formula as velocity V equal to omega by beta. Right? So from this, we can use either of these two formulas, 2 pi by lambda, or sometimes beta equal to omega by velocity. Right? So omega value, now to find omega, 2 pi f is required, and f is also given, that is beta. Now from this, beta need to be evaluated as beta equal to 2 pi f by velocity. So that equal to 2 pi into f value is given as 2 megahertz. 2 into 10 power 6 is the value of f, by velocity is to be given as 0.6 into c, where c is the velocity of light in free space and its value need to be considered as 0.6 into 3 into 10 power 8 meters per second. If we simplify the total equation, we will be getting the value of beta. And this beta and this 30 meters need to be multiplied and we'll have some finite value, and that should be considered as your tan of beta L value. Now finally, input impedance can be expressed as the complex form as real term plus imaginary term. Right? So this is the way, means how we have evaluated, means again the transforming of polar forms as well as into the rectangular form, like that. Finally, the input impedance need to be expressed in terms of complex form, okay, consisting of both real and imaginary parts. Next, a transmission line of characteristic impedance of 600 ohms is terminated by a reactance of J 180 ohms. Find the input impedance of a section 25 centimeters long at a frequency of 300 megahertz. So to find the input impedance of a transmission line, just now we have discussed in the previous problem, that is Zn is equal to Z0 into ZL plus JZ0 tan beta L by Z0 plus JZL tan beta L. See here, ZL value is given as characteristic impedance, means Z0 is equal to, that is 600 ohms is given, and terminated by reactance of, means ZL is equal to J 180 ohms only given. And in order to find this beta, again velocity equal to omega by beta you should use, and from this beta equal to omega by velocity, then this will be omega means 2 pi f by, and velocity value is 3 into 10 power 8 meters per second for the answer, and equal to 2 pi f value is 300 megahertz is given, that is 300 into 10 power 6 by 3 into 10 power 8 meters is. So this 10 power 8 and 10 power 8 gets cancelled, 3 gets cancelled, beta equal to 2 pi need to be obtained. And L value is also given, that is 25 centimeters. First we need to consider beta L value as 2 pi into 25 centimeters. So upon simplifying this value, we will be getting the value as beta L, and this need to be multiplied over here. Then finally, this Zin need to be expressed in terms of real and imaginary, and it should be measured in terms of ohms. Next, a low loss line with Z0 equal to 100 ohms is terminates in an impedance of ZR, that is 115 minus J 60 ohms. The wavelength of the transmission line is given as 3.5 meters. Means wavelength is represented with lambda and its value is equal to 3.5 meters is given. Using the given Smith chart, find the voltage standing wave ratios. So now to find voltage standing wave ratio, VSWR, or simply S is equal to 1 plus gamma by 1 minus gamma, right? So to find this gamma, we use gamma equal to ZL minus Z0 by ZL plus Z0, where ZL value is given as 115 minus J60 and Z0 value is given as 100 ohms. Now simplify, substitute over here and get the value. Then this is the case, gamma, modulus of gamma into e power j5. Magnitude as well as the phase functions need to be obtained upon converting the rectangular form into polar form. And this magnitude value need to be substituted over here to get the value of voltage standing wave ratio. Right? So this is the way we have solved, or we have analyzed some short answer type questions and the long answer type questions, and analytically which of the formulas are required to solve reflection coefficient and the standing wave ratio, along with how to find input impedance of a transmission line with the help of characteristic impedance Z0 and the load impedance of a transmission line if the length of the line is given case.
Like, share and subscribe. Hit the bell icon for more updates.